and welcome to the 59th online Spintronics seminar. It's my great pleasure to introduce our speaker today. Professor Chris Leighton received his BS and PhD in physics in University of Durham, UK. After postdoc research at UC San Diego with Professor Ivan Schuler, he joined the Materials Science Department at University of Minnesota in 2001. He is now Distinguished McKnight University Professor and grad faculty member in physics. He is a fellow of APS IEEE and Neutron Scattering Society of America, and the lead editor of the journal Physical Review Materials. So without further ado, Chris, please take it from here.
Okay, thank you very much, Shin, for the nice introduction, and Kirill and Shin for organizing this, or very nicely organizing this. I'm really impressed, and it's an honor to have a chance to speak to you today. So I will tell you about work that's going on in my group in electrolyte-gate-controlled magnetism. This is done at the University of Minnesota, as Shin mentioned, and I'll thank people who were specifically involved in the work when we get to the end. But up front, I'd like to acknowledge the agencies that pay for it. That's the National Science Foundation here in the US, through our Mercek Center on campus, and also from some parts of the work that I will talk about that are involving scattering. It's the Department of Energy. Okay, so here's an outline for what I will talk about today. I have a very quick introduction to magnetic perovskite oxides. I think that's something that probably many of you will have familiarity with, so I won't spend a long time on it. But then I will go into a little bit more depth about electrostatic control, which is what I'm going to try and talk about today, specifically using electrolytes and ionic liquids and gels. I'll tell you about some open issues with this technique. I'll tell you then about the material that we've been using for most of our experiments, which is this one here, this cobalt-based perovskite oxide. And then I'll show you what we've learned about mechanisms of how the gating works, electrostatic versus electrochemical mechanisms. And then the main goal of my talk is to show you how we've been able to use electric fields, both electrochemically and electrostatically, to control magnetism. And then at the end, I'll spend a few minutes showing, just so that this vignette on something that we've done very recently, which is in a slightly different type of material, which I think is pushing in a very interesting direction, which is to voltage-induce ferromagnetism, even from non-magnetic starting points. Okay, so oxides, perovskites in particular, I'll spend a lot of time on. Probably many of you are familiar with this base perovskite structure. This is the undistorted cubic structure, where we put a transition metal here in the center of this cubic unit cell. We have oxygen that forms an octahedral cage around that transition metal, and then on the corners of the cube, we put an alkaline earth or a rare earth material. And the reason there's so much interest in these perovskites is really their very diverse electronic and magnetic properties. So if we put copper here on the B site, this is the basic structural unit that makes up high temperature cuprate superconductors. If we put cobalt or manganese, as I'll talk about today, we get ferromagnetism with high spin polarization. This structure also supports colossal magneto resistance and then many types of multiferroics. So as an example, what I show here in the top right is one of the best understood magnetic perovskites. It's lanthanum strontium manganite, or LSMO. I show you its phase diagram. So this is temperature as a function of substitution of strontium for lanthanum. And what's happening basically in this phase diagram is on the left side, because lanthanum is trivalent, we have manganese 3+. On the right side, because strontium is divalent, we have manganese 4+. So as we dope one hole per unit cell to traverse this phase diagram, the point is that there are about half a dozen different electronic and magnetic ground states. So what I will talk about today is the concept that we could map a phase diagram like this using one sample, instead of the 20 or so that we used here. And if we were able to do that by electrostatically inducing that hole rather than chemically doping that hole, then we would have gained control over things like ferromagnetic curing temperatures, antiferromagnetic Néel temperatures, insulator metal transitions, and so on, which would potentially be of high interest for technology. So how could we possibly do that? Well, what I'm going to talk about today is a variant. It's a pretty radical variant, but nevertheless, it's a variant of a very old device, the MOSFET, the metal oxide semiconductor field effect transistor. So the idea there is that we take some semiconductor like silicon, we have a dielectric on top of it, and then a metallic gate on top of that. We apply a voltage across that dielectric, could be positive or negative. We produce an electric field that could point up or down. And when that electric field goes into our semiconductor, it has to be screened. And so we electrostatically induce, by the electric field effect, electrons or holes depending on the sign of the voltage. This is different than chemical doping because we're doing it here by generating the electron and holes without having any chemical substitution. You can then measure the impact of that electrostatic doping by flowing a current between the source and the drain. So what's wrong with just taking that very simple principle and trying to apply it to a material like a magnetic complex oxide? Well, if I take something like the phase diagram of that manganite that I just showed you, and I project it onto a two-dimensional charge axis, then it turns out that to be able to tune across the entire phase diagram, we would need something like 10 to the 15 holes per square centimeter. Now, to put that in context, a standard SiO2 gate dielectric will break down at about 1 times 10 to the 13. So there's a 2 order of magnitude gap between what we can do with conventional dielectrics and what we need in order to be able to manipulate materials like manganites. So this is a problem. The other part of the problem is obviously this doping is a surface effect, an interface effect. These charges hug this interface. How deep do they penetrate? Well, that's controlled by the Thomas Fermi screening length. These materials have much higher electron and hole densities than conventional semiconductors. So this length scale ends up being very short, 1 to 3 unit cells. So if we want or expect a volumetric effect in this film, we're going to need it to be just a handful of unit cells thick, which is going to introduce a whole bunch of other challenges, okay? So how do we address this? Well, in this talk, I'm going to talk about doing this using electrolyte gating in a device called an electric double layer transistor, or an EDLT. So the basic idea is we're going to take some film. In our case, it's going to be a perovskite. It'll be on some perovskite substrate. We're going to wire that thing up for an electrical transport measurement. And then on top of it, where we would normally have a dielectric in a standard MOSFET, we're going to replace that with an electrolyte. So I mean here a material that's got ionic conductivity, but no electronic conductivity. So we're going to have highly mobile ions. And then the idea is when we apply a voltage, we'll call it a gate voltage, across that new dielectric material, the electrolyte, then the ions in the electrolyte will move. Let's say that voltage is positive. Then cations will be driven down to the surface of our magnetic oxide. They won't be able to penetrate, so they'll accumulate in a sheet. And on the other side of the interface, we'll induce a controllable density of electrons. We'll electrostatically dope our material. Now, the beauty of this is that this thing that forms, which is called an electric double layer, is essentially a nanoscale parallel plate capacitor that completely decouples the thickness from the capacitance. It generates very large capacitance, as much as 100 microfarads per square centimeter. And if we then just use Q equals CV, that translates at just a few volts to as much as 10 to the 15 electrons or holes per square centimeter. It's 100 times more powerful, roughly speaking, than a conventional MOSFET with a standard dielectric. So what this device gives us is an external means to apply an electric field and accumulate charge densities that are at a significant fraction of an electron or hole per unit cell in most materials, okay? Now, great, but of course, the central question is what can we use as an effective electrolyte? All right, so I hope this isn't offensive to anybody who's a chemist or thinks about electrolytes on a daily basis, but if you don't, just as a reminder, how could I make an electrolyte? Well, you can make one very easily. You can go buy one if you want. Just take a salt, something like sodium chloride, put it into a solvent, something like water. You end up with highly mobile ions in a medium in solution that is an electrolyte, right? And anybody who's seen a TV advertisement for Gatorade knows that that's somehow good for you. Now, is it good for our experiments? Not particularly, because the solution here is in water, and water has a very small electrochemical stability window. You apply just a couple of volts and we can make hydrogen and oxygen, which is not good, okay? So are there better materials for us to use? There certainly are. There's an enormous class of compounds, it turns out. They're called ionic liquids. And what they are is essentially molten salts that are composed of large, mostly organic, bulky asymmetric ions. These ions are bulky and asymmetric to the point where they can't close pack. Because they can't close pack, they have low forces of interaction, which makes them molten already at room temperature. There's no solvent here. They're 100% concentrated. They're essentially liquid versions of sodium chloride at room temperature. The beautiful thing about them is because they're liquid, they have very high ionic mobility, and they have a really wide electrochemical stability window. So we can apply multiple, like 3 or 4 volts, positive or minus, to these materials before they undergo any degradation, okay? You can also make them solid, so you can keep all of the functionality of an ionic liquid. you can bring it into the solid state in a material called an ion gel. That's basically a polymer matrix. It can be as little as 10% by volume of the sample. The ionic liquid impregnates that polymer. The ions can move freely in the polymer. We have high ionic mobility, high capacitance, but you have a stiff, rubbery, processable solid state material. In fact, the way we use this is we spin cast it on a sacrificial wafer. It's something like 50 microns thick. We can then cut it with a blade. We can literally pick the material up with tweezers. It's rubbery. And then we can laminate it in what we call a cut and stick process on the surface of any material that we're interested in building a transistor from. So it's a very, very simple, elegant way to build an electrolyte gate transistor. It turns out these things are really powerful. So actually, this is a topic with a very long, very interesting history, but it really got going, at least in magnetism and in the field of oxides and superconductivity, about 2008. The Wasser's group really deserve an enormous amount of credit for this. They took a strontium titanate insulating wafer. They put an electrolyte of the type I showed you, or similar to it on the previous slide. They applied 3 volts, and they generated enough electrons on the surface of the strontium titanate to make it metallic, and even it went superconducting. Subsequent to that, there were some beautiful experiments done controlling superconductivity in the cuprates. This technique was used to discover superconductivity in potassium tantalate. And of course, it wasn't long here, this is over 10 years ago, that the first experiments were done on manganites. This is lanthanum calcium manganite, where it was shown that you can manipulate the Curie temperature by 10 or 20 Kelvin by applying a gate voltage, okay? A couple of colleagues and I got heavily into this in organic semiconductors. I won't dwell on that, but I will dwell on this interesting situation in vanadium oxide, right? So these 3 groups published in 2012 that they had just with a single volt completely controlled the famous temperature-dependent metal insulator transition in vanadium dioxide. This was a very big, important achievement. But just a year later, Stuart Parkin's group, they showed that those experiments could be reproduced, but that they depend very sensitively on the oxygen pressure during the measurement. And the implication here, very directly, is that the mechanism probably involved oxygen vacancies, not the creation of electrons and holes. So this triggered a controversy which to some extent has never really been fully resolved. Is the mechanism electrostatic or electrochemical? So the initial bias, if you'll pardon the pun, was that it would look something like this, simple electric double layer charging, like I just talked about. But we now know from a lot of experiments on a lot of systems, including oxides, that electrochemistry often occurs. In an oxide material, for instance, the electric field at that interface is so big that it can remove negatively charged oxide ions, forming oxygen vacancies, doping the material that way. And then when the electric field is reversed, these oxygen ions can be driven back in. They can annihilate the oxygen vacancies, and we get a reversible cycling mechanism that has very little to do with simple electrostatic charging, okay? Now, I really want to emphasize in my group, and certainly throughout this talk, you will see that we're certainly not shooting for electrostatics and trying to avoid electrochemistry. We're really embracing both. And the reason we do that is because we think the electrochemical mechanisms actually have really broad appeal. So they've actually produced some of the widest property modulations using any technique like this. They're not limited by screening. That opens up the world of gating metals, which has become quite an active field. There are multiple ion types that you could imagine using. You don't have to use an ionical liquid. You could use a solid electrolyte or an ion conductor. And the standard criticism has always been moving ions will be slow. Well, of course, the ions here are moving over very small distances. In fact, in 2021, it was recently reported that the fastest ionically operating transistor was now functioning at greater than 1 megahertz, which I think is easily fast enough for a lot of things. Not everything, but for a lot of things. So these have all contributed in some way to this new field, which I personally find very interesting. It's called Magneto Ionics, where the goal is to apply electric fields with very little associated current, and through low power control magnetic elements through the motion of ions in some way, using electrolytes or ion conductors. And then, of course, this has many potential applications. One big area that people are quite excited about is the possibility that we can do useful things here in neuromorphic computing. Okay, so in that context, what I'm going to talk about today is electrolyte-gated magnetic perovskites. I'll try and understand this issue of electrostatics versus electrochemistry. I'll show you we've done that by developing Operando probes, and I'll show you quite a bit of our work trying to use this to control ferromagnetism. All right, so with that, let me tell you a little bit about the material that we use for most of our experiments. It's this cobalt-based perovskite. We got interested in this material in this context really for two reasons. One is it contains formally cobalt 4+ ions. That's very electrochemically active, which is a good system for that reason. The other is the magnetic phase diagram shown here, and I won't go through the magnetic phase diagram in a lot of detail. I don't think I need to, but what I will point out is this is a classic example at low doping of a magnetically phase separated system. So when this system is lightly doped, it forms these ferromagnetic hole-rich clusters that live in a non-ferromagnetic insulating matrix. And then there's a percolation threshold at about 18% doping, X is 0.18, where those clusters connect into a long-range ordered ferromagnet. So we get a transition from a glassy insulator to a ferromagnetic metal. The Curie temperature at X equals 0.5 is about 250 K. It goes all the way up to above room temperature at X equals 1. So what drew us to this was the possibility that we might be able to sit just underneath a percolation threshold and then gate across it with an electric field and get an anomalously large increase in Curie temperature, saturation, magnetization, and so on. Okay, so I will show you that towards the end of the talk. To start with, I'm going to start somewhere simpler. We're going to be working here at X equals 0.5, where the system's a uniform ferromagnetic metal. We're going to make thin films that are deposited on a lanthanum aluminate substrate. They're going to be exactly 8 unit cells thick. 1 unit cell less than that, we start to get dead layer problems, so we can't maintain ferromagnetism so easily. And then I really want to emphasize, we have a side gate. That means that we have put the gate millimeters, in some case centimeters away from the channel. That dramatically slows down the operation of the device by many orders of magnitude. Why do we do that? Well, for this fundamental study, we're actually going to be bringing in X-rays and neutrons and scattering them from this interface. So we didn't want the gate on the top. Okay, if we were to put the gate on the top, we could dramatically increase the speed of the device. So don't worry too much about the very slow timescales. And then we use these cut and stick ion gels. And if you're interested or you know the field, the ionic liquid that we're using is the one that's shown here, and the polymer is a fluorinated blood polymer. Okay, I won't mention much at all about synthesis. I'll just briefly point out that we deposit epitaxial films here using high pressure oxygen sputter deposition, very high quality epitaxial materials. We characterize them by all sorts of methods. There's a lot of very interesting science that comes out of the transmission electron microscopy with atomic resolution in cross-section. But again, it's not completely relevant to what I'm going to talk about today. So I will essentially skip that in the interest of time. All right, so the experiments I'll show you first are aimed at helping us understand what the real mechanism is. Is it electrostatic or is it electrochemical? And our impression from the beginning was that we would find that it's in fact one or the other. And I'll show you, in fact, that in the same material, we most definitely get both. And we can control that by the way that we apply voltage to the device. So this is the simplest kind of experiment one can really do. We're sitting here just underneath room temperature. We are in an inert gas, argon. We're applying voltages. They could be positive or negative. And we're measuring the resistance change of the device. So here the ions are mobile and we can measure a time response. So if we apply a negative voltage, we get exactly what we expect. So -1 volt, this material's hole doped. You apply a negative voltage, you should accumulate more holes. So the resistance should drop, it should saturate, and then when we turn the bias off, it should go back to exactly where we started. But if you go to too large a negative voltage, something like -4 volts, what happens is you get a larger gate-induced resistance change, but when you turn the bias off, it does not recoil to the t equals 0 value, but goes to a resistance which is bigger than when we started the experiment. And then different again, if you apply a positive voltage, even a small one, delta R changes sign, you expect that. But when you turn the bias off, you find that it was almost entirely non-volatile. So to track these things versus voltage, we define 2 parameters, this gate-induced resistance change and this non-volatile change in the resistance, and plot them here as a function of gate voltage. This is both in argon, an inert gas, and now also in oxygen. And the most striking thing I think about this is the massive asymmetry between positive and negative bias. So in particular, a positive bias, we can get very large gate-induced changes. They actually go way off the scale of this plot, but they're almost entirely non-volatile. And when we put the device in oxygen, we can strongly suppress the effect. This isn't proof. I'm going to show you more proof later. But this is a strong hint that what's going on at positive voltages is electrochemical. We form oxygen vacancies and thereby control transport and magnetism. I'll show you. On the other hand, at negative voltages, there's a significant window where the non-volatility is very small. And it's not until we go to the largest negative voltages that we get anything that looks like a non-volatile response. This is a suggestion that at least over a significant window, we could have something which is predominantly electrostatic, not influenced by the oxygen. And again, this is not proof, but it's something that I will return to later on. So we're going to show you a number of other probes that really emphasize this. But before I do that, I just want to point out that that preliminary conclusion is completely consistent with the known redox stability of this and many other magnetic oxides, right? So we're dealing here with cobalt 4+. It's been known since the 50s that this is very unstable towards the formation of oxygen vacancies. The material is primed to form oxygen vacancies. So when we put on positive voltage, we have the electric field oriented in the right direction to remove a negatively charged oxide ion. And that's exactly what happens, aided by the low enthalpy of formation of the oxygen vacancies. But by the same token, when we reverse the electric field, it's unlikely that we can annihilate those very thermodynamically stable oxygen vacancies, but we have to balance charge. So the only option is to then accumulate holes on the cobalt. The cobalt valence goes up from 3.5 to 3.6 to 3.7, let's say. That's fine, but the minute we turn the bias off, then of course it becomes unstable again towards the formation of oxygen vacancies, which qualitatively explains the trends that we saw in those experiments. I'll point out another couple of things about this very simple idea. One is that subsequent experiments on the nicolates essentially came to the same conclusions. And of course, this has something trivial, but I think nevertheless important to say about these high-profile cases like strontium titanate and vanadium dioxide. Those are materials that are N-type. They can only be turned on in the positive bias direction because they only have significant mobility for electrons and not holes. And that means that they have to be operated in the direction where it's very likely that one can form an oxygen vacancy under the electric field, okay? All right, so that's fine, but it would be nice, of course, to really prove, rather than just using transport, that this is what's going on in our device. So we went to Operando probes that we can use of working devices. The first of these that we developed is Operando Synchrotron X-ray diffraction. So here we're using high energy X-rays. It's very easy to penetrate tens of micron thick ion gels. We can scatter from films that have thicknesses, let's say 28 unit cells, and get enormous signals. And we can do very simple experiments like specular X-ray diffraction. So this shows here the LSCO film peak, now measured in situ as a function of the gate voltage. And what we basically find is we apply negative voltages, almost nothing happens in this material. But as soon as we apply even a small positive voltage, the entire peak uniformly shifts to the left. That tells us, of course, that we have a lattice expansion, and that's plotted here. This is the change in the C-axis, or the change in the cell volume as a function of gate voltage. And hopefully this asymmetry I was talking about is now very clear. So we can barely detect any structural change at negative voltage, but by applying just a couple of volts, we get a 1% expansion of the cell volume. It's an enormous expansion of the cell volume. So when we saw this, our first thought about it is LSCO one of the many oxides that undergoes this famous chemical expansion effect, where oxygen vacancy formation increases the size of the unit cell? So we checked this using a bulk technique called thermogravimetric analysis. We're basically just measuring the mass. We're warming it up in a reducing environment. We lose a certain amount of mass, which tells us what oxygen deficiency we have. We do that progressively to higher temperatures. We end up with a whole series of samples where we have known oxygen deficiency. We can then do powder X-ray diffraction, and we can pull out what is the change in the cell volume as a function of delta, the oxygen deficiency. And you can see, indeed, this is one of these many materials that undergoes this nice uniform linear expansion of the lattice when oxygen vacancies are formed. And the significance of this is if we have an operando measurement of the cell volume versus voltage, and we now know how the cell volume responds to oxygen deficiency, you can just put those two things together and we can predict or estimate the change in oxygen deficiency that's being generated by the gate voltage. And it turns out with just 2 volts, we're already getting 0.16 missing oxygens per unit cell. We actually stopped here at 2 volts. We should have kept going. I'll show you later on that if we go out to something like 3 and 4 volts, we can actually get to 0.5 missing oxygens per unit cell, at which point something really interesting happens, which I'll get to in a second, okay? Now, one of the things that really surprised us about this is we're applying a surface electric field. The film's quite thick, it's 16, 17 nanometers thick, and yet it looks like the entire X-ray diffraction pattern shifts. It looks like the whole film is being reduced all the way through its thickness. So we were a bit skeptical about that, so we decided we would apply a depth-sensitive probe, and we used polarized neutron reflectometry, PNR. So this is, in principle, fairly simple technique. We're going to be reflecting neutrons from the surface of our magnetic material. Neutrons are, of course, have finite spin, so we can polarize them what we call plus, meaning they're parallel to the magnetization of our material. We can orient them minus, which is anti-parallel to the orientation of our material, and we can analyze their polarization on the way out so that we can plot the neutron reflectivity as a function of scattering vector. This is at low temperatures in a saturating field here in 0 volts. And we plot 2 channels in this graph, what we call the plus plus and the minus minus, meaning we're bringing in parallel neutrons, counting parallel neutrons out, or bringing in anti-parallel neutrons and counting anti-parallel neutrons out. And there's a difference between the plus plus and the minus minus, and it oscillates. And that's caused by the fact that we have a ferromagnetic film, right? So what's encoded in here is the Fourier transform of the depth profile of the magnetization. So we can pull out the magnetization by refinement as a function of depth. So here's our substrate. This is our oxide film. This is in 0 volts, then 2 volts, and then 3 volts. And our electrolyte is on the top of the film out here. So you can see, I mean, we did account, we allowed for a 2-layer model for the possibility that there's a little bit of a gradient towards the top. But basically, we're applying a surface electric field here, and we are, in fact, getting significant magnetization reduction caused by the formation of oxygen vacancies way at the bottom of the film. We can also estimate from this magnetization what the oxygen deficiency actually is, and we find that it's in really good agreement with what we got from synchrotron X-ray diffraction, okay? So what we're doing here is we're basically taking a material that's got a ferromagnetic Curie temperature of about 230 Kelvin. By applying a voltage, we can dial up any TC we want down to essentially 20 or 30 K. Now, key question, if we then go to negative voltages, can we revive the ferromagnetism and make a uniform cycle? And I'll show you in a few minutes here that we can, okay? First, I just want to answer the question, how is it that we can apply a surface electric field up here and get this redox activity at the bottom of the film? So again, this is a very simple picture that we've developed. This is what we believe our electric double layer looks like at positive voltages. We have an electric field that looks like this. We believe that what happens at the very top surface is the electric field assists the formation of oxygen vacancies by lowering delta GV0, which is already very small. That puts oxygen vacancies in the top 1 or 2 unit cells. And then we have a chemical potential gradient for oxygen. And the remarkable thing about the cobaltites, the really amazing thing about the cobalt-based perovskites, is oxygen vacancy diffusion is basically fast enough to do the rest. Even underneath room temperature here at 260 Kelvin with the known diffusion coefficients that have been measured in this material, the diffusion length for oxygen vacancies is safely thicker than the film. If we work at something like 300 Kelvin, it's actually many times the thickness of the film. So it's no mystery that we're able to do this. We're able to do this because the materials are very, very good oxygen transporters. So this has really put a spotlight on the cobaltites in the literature on this topic. In particular, X equals 1. So this is one of the end members of this compound. I mentioned to you that it's a cubic perovskite. It's ferromagnetic with this around room temperature TC. But also there's this really beautiful gift, which is if we make oxygen deficient to the level of half an oxygen per unit cell, it turns out there's a vacancy ordered phase that forms. It's called orthorhombic Brown-Millerite, and it couldn't be more different magnetically. It's an antiferromagnetic insulator. And one can drive this transition with gating back and forth between the perovskite and the Brown-Millerite, between a ferromagnetic metal and an antiferromagnetic insulator. This has now been shown in these papers that I highlight here. So it's been shown by Operando X-ray diffraction, for instance, that we can go between Brown-Millerite and perovskite. One of these things is an insulator. The other one is really a metal. One is ferromagnetic, and the other one is an antiferromagnetic insulator. What we have shown recently is that we can also do this even at x equals 0.5. And that's actually quite important because unlike at x equals 1, at x equals 0.5, these materials are air stable in both forms. The perovskite and the brown millerite are both air stable. So we can start with a perovskite film. We can put on an ion gel. We can apply voltages. We can completely eliminate the perovskite phase, turn on a brown millerite phase. As we do that, we can controllably decrease the magnetization as it goes towards the antiferromagnetic insulator. We can kill the material's Curie temperature. And then I think most interesting, when we measure the source drain current in a transistor, we start in a perovskite phase where it's a high current, it's a highly conductive material. We can drive it to the brown millerite with a 10 to the 6 on-off ratio. And then we can come back and we can rejuvenate this and go back to the perovskite phase to the ferromagnetic metal, again with a 10 to the 6 on-off ratio. Now, I should emphasize that those previous papers that I highlighted on that slide before showed this happening over a few cycles. We can also do it over a few cycles, but I don't want to gloss over the fact that if we go to a larger number of cycles, we see endurance problems. We see specifically that it's relatively easy to go to the brown millerite, but can become progressively more difficult to get it back to the fully oxygenated perovskite. There are some strong hints in the synchrotron X-ray diffraction data about why that might be, and this is something that we're working on in my group actively right now to try and understand the details of that process. But hopefully this certainly shows that we can make quite radical variations in the magnetic property of a material happen using electrochemical gating in this kind of technique. We were also interested, however, to do the exact opposite, which is to start from 0 volts. I showed you that by going to negative voltages, we were able to get a predominantly electrostatic effect. We were interested, is it possible there to get reversible control of magnetism also? So here I'm going back to the films that I showed you at the beginning of the talk. This is 8 unit cells thick. We're applying now only negative voltages. We get a modulation of about 20% of the resistance. It's quite small. And then there's also an inflection point in here that tells us about where the Curie temperature is in this material. So we can expose that just by plotting the derivative of d rho by dt. You can see that by applying -4 volts, we get about a 12 Kelvin shift in the Curie temperature. Now, if we measure the anomalous Hall coefficient, turns out this material has quite nice anomalous Hall conductivity, so we can also probe magnetism that way. We can measure the anomalous Hall conductivity as a function of temperature, as a function of voltage, and you can see here nice proof that we get about a 13 Kelvin shift in the Curie temperature. So I know what you're thinking at this point. I just showed you that we could do it over hundreds of Kelvin with electrochemistry. Why do I care that we can do it here with 13 Kelvin with a predominantly electrostatic method? But we didn't yet execute the idea I showed you right at the beginning of the talk, that we might be able to go under the percolation threshold and then gate across that percolation threshold and get a larger change in the magnetic properties. So this is what I'll show next. I think I'll gloss over here, unfortunately, the theory of this. This was published in PRL in 2017. Very nice work by Boris Shklovsky and Rafael Fernandez, our collaborators. What they basically did is percolation modeling. And they showed us that our original idea wouldn't really work. You have to be incredibly close to the percolation threshold to be able to gate across it. But what they also showed us is if you just keep the doping high and you go down in thickness to the 2-dimensional limit, you go under the percolation threshold that way, essentially going into the dead layer, then it should be much easier to gate it then back into a ferromagnetic state. So we tested this in our experiments. The first step was to keep the thickness constant here at about 10 unit cells, so relatively thick. And then we go from chemical dopings of 0.3 down to 0.15 and eventually 0.10. And you can see, certainly we go into an insulating state. We apply a voltage, we certainly get a gate effect, but it is nowhere near big enough to gate across an insulator metal transition, as was predicted. In fact, even if we're at 15/17 of the percolation threshold, right, we were still not able to gate across the insulator metal transition. So at that point, we did what we were essentially taught by our theory colleagues. We decreased the thickness from 8 to 7 to 6 to 5 unit cells. And it turns out 6 unit cells below, we get exactly what was predicted. So we go into an insulating non-ferromagnetic state. And then as we apply -1, -2, -3, -4 volts, we can drive it through a percolative insulator metal transition. And of course, the interesting thing here is, does ferromagnetism come along with this? So we tested that again using the anomalous Hall effect. This is at 5 Kelvin. We're applying voltages now through -4 volts. And you can see we start from something where there is no anomalous Hall. We progressively turn it on to the point where we end up with a really robust ferromagnet. I want to emphasize it's got a 1 Tesla coercivity, has perpendicular magnetic anisotropy, has remnants. It's about 50% of the saturation, magnetization. All these things are important. And I'll point out that we also directly verified this using polarized neutron reflectometry. So if you're not very trusting of the anomalous Hall effect, it was verified to be long-range ordered ferromagnetism. We also then measured the Hall conductivity as a function of temperature. You take it from a system where there's almost none to the point where you can generate a TC, which is at least 150 Kelvin, okay? So to put that in context, for a predominantly electrostatic effect, not an electrochemical effect, that's actually the highest that I'm aware of electrostatic TC shift at any complex oxide by any method. And it's the highest electrostatic TC shift by electrolyte gating that I think has been achieved on any material. Certainly, I think it was at the time we published this in 2018. Okay. All right. So with that, let me just spend my last maybe 7-8 minutes or something like that talking about taking this same technique, applying it to very different materials to address a different question, which is voltage-induced ferromagnetism in a diamagnet. Okay. So this really was driven by us sort of taking a step back and looking at the field of Magneto Ionics from a bit of a distance and realizing that essentially everything that's been done, and there's been some really amazing work by many people, everything that's been done falls in one of two categories. There is the work where you take a known ferromagnet and you use voltage to control its properties like anisotropy, switching, coercive field, or so on. This is very important. It can be done at room temperature. I think it's the closest to a technological application. Or there are the kind of work that's been done where ferromagnetism is induced by the voltage, starting from some other magnetic state, like an antiferromagnet, which is ordered, or a disordered state like a paramagnet. And this got us wondering, are there any conditions under which we could voltage-induce ferromagnetism from a diamagnetic starting point, rigorously non-magnetic material with spin 0? So this drove us to thinking about Pyrite Ion Disulfide. So you may be familiar with this material. It's fool's gold. You may know the crystal structure. You may know the obviously goldish appearance of this material. You might also realize that chemically it's a little bit interesting because it's iron 2+, sulfur 2, 2-. So that gives you a T2G6 Eg0 electronic configuration. Its S equals 0. Rigorously, it is a diamagnet. This has been known for decades. And it's a 1 electron volt band gap semiconductor, actually. Okay. Now, if you go one element over in the transition metal disulfides, this is the global phase diagram. If you go from iron disulfide to cobalt disulfide, then you add 1 electron in this Eg sublevel that produces spin of a half. It becomes a ferromagnetic metal. It has a TC of about 120 Kelvin. Now, what's really incredible about this is if you make alloys between iron disulfide and cobalt disulfide, putting in as little as 1% cobalt disulfide induces ferromagnetism, and the TC of that ferromagnetism races up. It becomes about 150, 160 Kelvin eventually. So you have diamagnetism in iron disulfide, but it lives very close to a ferromagnetic ground state, and it led to us wondering if, without adding magnetic cobalt dopants, but just by adding electrons on the surface using our technique, could we ever induce ferromagnetism in this material from a spin 0 starting point? Okay. So this is what we tried to do. We did it in a fairly crude way. This is a bulk single crystal of iron sulfide. It's in an ionic liquid this time as the gating medium. We're applying only positive voltages. We're trying to induce electrons in the iron sulfide. And there's a bit of a wrinkle with the transport in this material in that it exhibits surface conduction. So when you look at resistance as a function of temperature, there's this crossover, a little bit like a topological insulator, between the bulk conduction, which is N-type, and a surface shunting, which is P-type. But just ignoring that, it is just literally sort of a distraction. What happens when we apply positive voltage is we can drive this beautiful insulator metal transition. So we're adding electrons here, driving it to a metallic state. And I should emphasize, we can apply 3 volts, go back to 0, 3 volts, go back to 0. Completely unlike the oxides, this is entirely volatile and entirely reversible. Everything points to this being a simple electrostatic induction of electrons. If you're interested in why it's so different than the oxides, please ask about that. That's something I think we have concrete ideas about why pyrite responds so differently than the complex oxide materials. But the question here, of course, is when you drive that insulator metal transition, do you see anything in the magnetism? So we went to the Hall effect again. This is at 30 Kelvin, going from 0 volts to 3 volts. This is the Hall conductance plotted as a function of field. The starting state, that surface state, turns out to have very low mobility, so there's almost no Hall coefficient. And if you blow up what happens here at low voltages, you turn on a negative Hall coefficient. So it looks like you're putting electrons on the surface of the material, and then very abruptly, at about 1.8 volts, out pops this huge positive Hall coefficient. And that huge positive Hall coefficient, it's nonlinear, it's sigmoidal in shape, it saturates with field. If you go down to the lowest temperatures we measured, which is 1.8 Kelvin, and look at that in a bit more detail, it turns out, in fact, the loop really does open. So you end up with finite coercivity and finite remnants. If I plot just one curve for you here at 3 volts, 1.8 Kelvin, it looks like a very nice anomalous Hall effect of a ferromagnetic material. And I have to emphasize that it is a positive anomalous Hall coefficient, which is the same sign as we get in bulk cobalt-doped ion disulfide. So you have a nonlinear sigmoidal shape Hall effect. It has the right sign. You have finite coercivity, you have finite remnants. It really looks like you've been able to induce ferromagnetism, okay? And also, you can measure the coercivity as a function of the temperature. Multiple samples here. As we go up in gate voltage, you see the coercivity just dies as we would expect. It looks like the highest TC that we're able to get in this material is about 25 Kelvin, but it's being induced not only from a state that has TC equals 0, but also from a state that initially had spin 0, right? Now, there are certainly things that we don't understand. In particular, the temperature dependence is very interesting. So if we look at the temperature dependence at high voltage, you have this nice anomalous Hall signal. The coercivity disappears at 25 Kelvin. We believe that to be the Curie temperature. But it turns out that the anomalous Hall effect goes more than 10 times higher than that. It goes up to 280 K. So it looks to us like there are strong ferromagnetic interactions, even if the system is not in a long-range ordered ferromagnetic state. And we have some ideas about why that might be. It could be related to Mohn-Wagner physics, because we have here quite a soft ferromagnet in a very two-dimensional limit. It could also be that we have superparamagnetism, and this is a blocking temperature, and the real Curie temperature is much higher. Either way, I think it points to the fact that 25 Kelvin is not the end of what we can squeeze out of this system. I believe we could really push higher in terms of ordering temperatures. We've also done some theory on this in collaboration with Taran Barol and Rafael Fernandez. I won't go through what's on the left. That's basically bookkeeping. We did check that the amount of charge that should be necessary to do that is conceivable in comparison to cobalt-doped ion disulfide, so that's a little bit dull. What's more interesting is we did some DFT plus U calculations where we calculate the magnetization that should happen in this material as a function of just adding electrons to the iron sulfide unit cell. And when you do that, ferromagnetism does turn on. It actually becomes highly spin polarized. You go up to 1 Bohr magneton per ion eventually. That happens at about 3 × 10⁻14 per centimeter square. And then importantly, we did a tight binding parameterization of that DFT calculated band structure so that we could calculate the electronic susceptibility. And that's shown here in the inset as a function of K, as a function of electron density. And as you go to high electron densities in this system, what is happening is a peak around the gamma point. So it looks like real long-range ordered ferromagnetism. And the point where this emerges is actually exactly where the Fermi level gets to a very narrow ion EG band in the conduction band. At that point, we think that what happens here is we're able to hit the Stoner criterion by accumulation of electron density alone. And that's how we're able to trigger ferromagnetism from a diamagnetic starting point. Okay, so with that, I think I'm on time for 45 minutes here. So I'll wrap up by saying, hope I've convinced you that these ionic liquids and gels in these electric double layer transistors really hold great promise. These and related concepts, I think, are really nice for tuning magnetic materials. Certainly electrostatics and electrochemistry both go on. We believe that they're both very powerful. We have good techniques now to try and tease them apart, so we can certainly understand this. And what I showed you here today in the cobaltites is using an electrochemical mechanism. We can basically toggle between a ferromagnetic metal and an antiferromagnetic insulator. Using electrostatic control, we can do not quite as well, but we can still modulate the Curie temperature over about 160 Kelvin. And then in our work trying to induce ferromagnetism in a diamagnet, we've shown that this is in principle possible. We've gotten to TC of only 25 Kelvin, but I think there's a lot of potential to go higher than that, even just in the pyrite system. We haven't looked at any others. Okay, I'd like to thank some people, 3 students in particular. Jeff Walter, a former student in my group who's now a faculty member himself at a local university, Augsburg here in Minneapolis. Vipul Chaturvedi, who's following from Jeff's experiments, and also Will Pastiglione, who's doing some of the reversible electrochemical studies that I showed you here. And of course, we'd like to thank our collaborators here at the University of Minnesota. And we're very grateful to the X-ray and neutron people that we collaborate with at Sources in order to get these scattering experiments done. With that, I'll stop. I'd be happy to take any questions, and I'll leave here this short list of papers if you'd like to read more about any aspect of this work. Thank you.
Thank you very much for this interesting talk. This talk is open for questions. If you have questions on Zoom, please use raise hand function. Or you can send me a private message and I can read it for you. If you're watching this on Twitch, you can type your questions on in the chat box. So the first question will be asked by Professor Xiahong. Please go ahead.
Hi, this is Xiahong from UNL. Very impressive work. I have a question about the electrolyte gating of the LSCO. So you mentioned this large effect is partly due to the very efficient oxygen vacancy efficiency, diffusion efficiency. So I was wondering, is it because oxygen vacancy also play a big role in other correlate oxides? So do you expect similar effect in manganites and nickelates?
Yeah, it's a good question. So the short answer is I'm not sure that anything will be better than a cobaltite in that respect. And the reason is this oxygen vacancy diffusivity, it is higher in cobalt-based perovskites than it is in many others. When we started this whole thing, we had, I think, a strong bias, just like everybody else, that probably the most important parameter was the enthalpy of formation of the oxygen vacancies. How easy is it to make an oxygen vacancy? We have completely reversed our ideas about that, right? We no longer think that that is the most important thing. We think actually the most important thing is the diffusivity. Once you generate with an electric field some oxygen vacancies on the top surface, if the diffusivity is big enough, they will proliferate. If the diffusivity is low, they won't. And this seems to sort of jive with everything that's in the literature. And in that context, the cobaltites are very attractive. Manganites don't have as high an oxygen vacancy diffusion rate. The other systems that can have very high oxygen diffusivity, interestingly, are cuprates. So for instance, in the 214 lanthanum strontium cuprate, that can have very high, even at room temperature, oxygen diffusivity. So we think that's the key variable. And we actually, I'd be happy to show you if you like, we published this. It's got nothing to do with magnetism, but we did go through the thought process. If we're right in that thinking, are there oxides where we can basically completely eliminate this effect because the diffusivity is tiny? And there are. One that we found is barium tin oxide, perovskite that has about 10 orders of magnitude lower oxygen diffusivity at room temperature. We did experiments on that, and it is entirely electrostatic. We can see no electrochemical effects whatsoever. They really seem to be totally shut off. So that's our view of why the cobaltites have generated so much interest in this vein.
Okay, thank you.
Yeah, thanks.
Professor Kai Liu, please go ahead with your question.
Great talk, Chris. I apologize, I got distracted in the middle. I don't know if you already covered it, but I was wondering, what is the time scale limit in your systems? Yeah,
so we use this side gate, right? And the reason we use the side gate is just for convenience, because we're bringing in X-rays and neutron beams and doing operando experiments. That slows things down by multiple orders of magnitude, right? Because we've literally put in some cases, we have a centimeter between the gate and the channel. So what we're doing right now, once we've learned how this works with the Operando probes, we're taking the side gate away using a top gate. And then we can take the electrolyte thickness down to something like a micron or even less. And there, I think we'll be able to see intrinsically, when we do something like trigger a perovskite brown millerite transformation, how fast can we run it? At what frequency could we run that kind of transformation? The answer is we don't know yet. You know, in our case, the timescales are really long, but it's just the side-gated device. In terms of fundamentally how well you can do, I can tell you that I have colleagues who are doing this, not in magnetism, but just gating semiconductors. And they have demonstrated this year that they can run an inverter circuit at actually more than 1 megahertz with an ionically operating transistor with an electrolyte gate. So, you know, the ionic mobilities are really huge. It's pretty trivial to calculate how far you can move them in 10 to minus 6 seconds. And that is feasible, and they've already demonstrated it.
Thank you.
So we got a long way to go for the magnetism to catch up, but I think, you know, there's no fundamental stumbling block.
Yep. Thanks.
Thank you, Kai. Yeah.
Professor Barry Zink, please go ahead with your question.
Hey, Chris, great talk as usual. Thanks. Nice to see you.
Thanks, Barry.
I'm interested by this high temperature Hall effect on the iron pyrite stuff. It seemed like both of the mechanisms you suggested for that required some sort of inhomogeneity or some, I forget the word you used exactly, but paramagnetism, right? This inhomogeneity, I mean, it's a bulk single crystal, right? So I'm interested if you have a thought about where that's coming from. Is it the inhomogeneity and the ionic gel itself that's somehow getting transferred?
No, it's a great question, right? And this is sort of the most interesting part of this, and it's what we're working on right now. So let me go through the two possibilities. One of them is Merman, in my mind at least, Merman-Wagner type ideas, right? Because we know how deep this layer is being accumulated. I can show you the calculations here on the next slide. We think that we have about a 2 nanometer accumulation depth. So 90% of the carriers are only 4 unit cells from the surface. So it really is confined to the surface. So we're in a 2-dimensional limit very much. If we're in the 2-dimensional limit and we have a soft ferromagnet, we only have hundreds or maybe thousands of Gauss of coercivity. It is possible that what's happening here is the system wants to order at very high temperatures. It has ferromagnetic correlations at very high temperatures, but it just can't order until low temperatures. That's one possibility to us. The other is the solid lines that I actually show here in this plot. They are fits to the Langevin equation. So they are fits to superparamagnetism, okay? And they work quite nicely. They don't work perfectly because it turns out that the size of the cluster is not constant as a function of temperature, which I see as a bit of a limitation. But if that is the right way to think about it, then what we have here is a blocking point, and we would have some, I believe, lateral inhomogeneity in the gating process that would be needed to make that. You can work out what the size of the clusters would be if they're 2 nanometers thick. They've got to be about 10 nanometers wide. So in this picture, there is inhomogeneity laterally on something like a 10 nanometer length scale. Where can it come from? We have a vapor transport chrome crystal. They have terraces. The terraces are a bit wider, actually, than 10 nanometers. They're typically something like 100 nanometers. That could be part of it. The other thing is, you know, like almost everybody in this field, we take an air-exposed surface and we put the ionic liquid or a cotton stick ion gel on top of it. So could it be that there are lateral inhomogeneities and we have little bubbles in there that are regions where it's better gated than others? I think that's certainly possible. So that could be producing the lateral inhomogeneity too.
So, but the ionic gel with this polymer stuff in it, you think that's totally uniform on that length scale? Yeah, so this particular experiment we've done with ionic liquid. So there's no inhomogeneity in the polymer that could play a role here. It would have to be the ionic liquid itself. And you know, you look at the length scales involved in those, and they would appear to be quite a bit shorter than that. There's not an obvious reason why that would be inhomogeneous. No, I was thinking of the polymer, but if it's a liquid, it's
Yeah.
hard to imagine that. All right,
Right.
sorry to take so much time, but thank you.
No, it's a great question.
There's a question from Twitch. I'm just going to read it to you. Thanks to Dr. Leighton for the interesting talk. Sometimes the ionic liquid can damage materials such as a bismuth selenide. What material can be used as a protection layer for this experiment?
Yeah, well, it's a good question. And you know, I should say from our experience, what the word damage actually means, first of all. So we certainly see what you could call damage at positive voltages in particular. Because the voltages I showed you here, we go through to about 3 or 4 volts. We make a lot of oxygen vacancies. If you keep going, you will exceed the electrochemical stability window of the ion gel, the ionic liquid. Bad things happen. We can also sometimes etch materials, right? We can literally get to the point where a positive bias, I think we have just so many H+ ions around that we're essentially acid etching the material. And maybe that's what the person who's asking this question is asking about. Can we use something as a protective layer? That's a really fantastic question. I know of one piece of work that's been done along these lines. David Goldhaber Gordon's group at Stanford has developed a technique to put some micron scale, very thin hexagonal boron nitride flakes in between a medium, a target material and an electrolyte. And he did that to boost mobility, but I think this is a potential way to moderate the electric field to potentially avoid the kind of damage that you're asking about. Are there other methods to do that? There are, and actually we are trying some chemical means to deposit very thin films that would not necessarily be 2D materials that could perhaps be scaled a bit bigger laterally. So that is research that's ongoing.
Thank you. Professor, I think that's Yu Jian, right? Please go ahead with the question.
Yeah, it's me. So I have a question about this. I probably missed the first part of your question, your presentation, but what's the mechanism of forming those oxygen vacancies, and how is that influence the iron disulfide case? Would it have oxygen vacancies in there?
Yeah, okay.
So the sulfur vacancy there, sorry.
Yeah. So in the cobalt types, we believe the mechanism for forming the oxygen vacancy is very simple. So the enthalpy of formation of the oxygen vacancies in that system is low. And it's so low that we believe when you apply an electric field, that basically the electric field is oriented in the right direction to pull out a negatively charged oxide ion. So it basically lowers the formation energy until we hit 0. Oxygen vacancies are formed spontaneously in the top layers. And then essentially diffusion is fast enough to do the rest. Now, diffusion might actually be aided by the electric field, but just as a minimum estimate, we just use, an electric field affected diffusivity. It's already fast enough. Okay. Now, in the sulfide, you're asking a very good question there, because in the sulfide we found no such evidence. And why is that? It relates to the question that Xiaohong asked here, which is, it is a whole different ballgame for diffusivity for sulfur vacancies. It turns out that sulfur vacancy diffusivity in iron sulfide is extremely slow. So we believe that's critical here. Could we be forming sulfur vacancies in the very top unit cell? It's absolutely plausible, but they won't proliferate. They won't move any deeper because the sulfur vacancy diffusion rate is incredibly small. So we believe it's really that rate of diffusivity of the species that can be made that controls whether you get a broadly electrochemical or electrostatic response.